Section 9. We're going to multiply binomials that have radicals. If you remember from Chapter 5, we multiplied these two binomials together. X minus 4 times x plus 4 equals x squared minus 16. As you know, this is called the difference of two squares pattern. We can apply this pattern to binomials that contain radicals. Consider this problem. We have 6 plus the square root of 11 times 6 minus the square root of 11. We do this problem exactly the way we did this one up here. 6 times 6 is equal to 6 squared. The square root of 11 times the square root of 11 is equal to the square root of 11 squared. Makes no difference whether this is a constant, a variable, or a radical. You square it and you keep the base the same, just like you did up here. You said 4 times 4 is 4 squared, which is 16. So here you say square root of 11 times the square root of 11 is the square root of 11 squared. Now we simplify. 6 squared is 36. The square root of 11 squared, remember the radical and the squared sign cancel, and you get 11. Watch the sign. 36 minus 11 is 25. Let's try this one. 5 plus the square root of 7 times 5 minus the square root of 7. 5 times 5 is 25. Square root of 7 times square root of 7 is the square root of 7 squared. These cancel. 25 minus 7 is 18. The reason, remember, why we just multiply the outer term, the first terms and the last terms, is that when you do the outer and the inner terms, you get 5 times negative square root of 7 plus 5 times square root of 7, and they cancel out. So you have no middle term. Also, don't forget that square root of x squared is equal to x if x is positive. Let's consider this problem here. We have 5 square root of 3 minus 6 times 5 square root of 3 plus 6. What is this equal to? Well, we have to square this right here, which is 5 times 5 is 25. Square root of 3 times the square root of 3 squared is just 3, as indicated right here. And then we have a negative 6 times a positive 6 gives you a negative 36. Simplify, we have 25 times 3 is 75 minus 36 equals 39. Let's look at another one. 2 times the square root of 5 plus 3. 2 times the square root of 5 minus square root of 3. 2 times the square root of 5 times 2 square root of 5 is 4 times 5. Don't forget that you've got to square the 2 also, because this is actually telling you 2 square root of 5, and the whole thing is squared, remember. Okay? So once we do that, we get 4 times 5 square root of 3 times the square root of 3, which is square root of 3 squared. It's just the radicand, 3. And then we simplify. 20 minus 3 is 17. When multiplying binomials that contain radicals and are differences of two squares, use this pattern. Key point to remember is this once again. Square root of x, quantity squared, is x. And we're going to assume that x is going to be positive. Let's take a look at this one. X plus 4 quantity squared. You should recognize that as a perfect square trinomial. We can also apply this to radicals. 3 plus 5 square root of 5, 3 plus the square root of 5 squared. This is the same thing as 3 squared, because you multiply the first term together, plus 2 times the first and the last term, which is 3 square root of 5, times 2. You got to double it. Look at the property here. says 2a times b. Here's the a, here's the b. So you're multiplying a times b, which is 3 times the square root of 5 right there, and then you have to double it. Now plus the last term squared. Square root of 5 squared. What's this equal to? 3 squared is 9. 2 times 3 is 6. Square root of 5 plus, and of course these cancel and you get 5 by itself. 5 plus 9, or 9 plus 5 is 14, plus 6 square root of 5, and that is your answer. Remember, under no circumstances can you add 14 plus 6. Why not? Because you have to do your multiplication before your addition. Now, if you're going to simplify this further, if it asks you for a decimal, then you change the 5 to a decimal number, multiply it by 6, and then add the 14. So follow the order of operation. Let's look at this one. Square root of 3 minus, or 3 square root of 3 minus the square root of 10, quantity squared. Another perfect square trinomial. 3 times the square root of 3 squared. So we'll take the first term and square it. The middle term is twice the first term times the second term. Here's the first term. There's the second term. And you have to do it twice, remember, because of this right up here. It says in the pattern 2 plus the square root of 10 squared. And the last term is the square root of 10 squared. Now, what's this equal to? Square root of 3 squared is 3. 3 times 9 is, oops, I made a mistake there. No, I didn't. This is okay. Minus 2, and then this is 3 times the square root of 30 times 2. 2 times 3 square root of 30 plus 10. 10 plus 27 is 37. That's how I get the 37. Minus 6. 2 times 3 is 6 times 30. So you ask yourself, can we do anything with 30? Well, there's no perfect squares in 30. Think of them. There's 25. No, that doesn't work. 10. I mean, not 10, 100. 64. 4. No perfect squares in 30, although you might think there would be, but there isn't. So this here is your final answer. Conjugates. Conjugates are the result of writing the sum of two terms as a difference, and vice versa. For example, a square root of b plus c square root of d, and this, a plus square root of b minus c square root of d, are called conjugates. And the product, interesting enough, will be an integer. It will allow us to get rid of the radicals. They differ in only in the sign of one term. Minus, plus. Everything else is the same. So a plus b and a minus b are conjugates. X minus 3 and x plus 3 are conjugates. And we use conjugates to rationalize binomial denominators. If you remember a couple sections ago, we had the term rationalize. It means to turn an irrational number into a rational number. And remember, you cannot have a radical in the denominator, and that's why we're doing this. So here's the problem. 3 over 5 minus 2 square root of 7. You just can't multiply by the square root of 7, because if you do that, you've got to multiply this times the square root of 7, and then you'll have 5 square root of 7 in the denominator again. So you really didn't get rid of it. So what you do is you multiply this by the conjugate. And the conjugate in this case is 5 plus 2 square root of 7. Here's a minus, here's a plus, everything else is the same. If you multiply the denominator by the conjugate, you got to multiply the numerator by the same thing. Now let's see how this plays out here. We have 5 times 5 is 25. And you multiply this by this, you get negative 2 square root of 7 quantity squared, because you're multiplying 2 square root of 7 times 2 square root of 7. The top number you distribute to 3 to the 5, and you distribute the 3 to the 2 square root of 7. I just haven't done that right up here yet. Okay. So we're going to keep this the same for a while, although you could distribute at any time. Let's look at the bottom. 25 stays the same, minus sign. And what happens here? We have 2 squared is 4, and square root of 7 squared is 7. Everybody see that? The square root of 7 squared is just a 7. Here I've distributed 3 from the first one. I get 15 plus 6 square root of 7. Simplify this bottom part here, and you get negative 3. We're not done yet, because I see that negative 3 goes into 15 negative 5 times, and negative 3 goes into 6 negative 2 times. So your final answer is negative 5 minus 2 square root of 7. Remember, at no time can you add these two together. You have to do your multiplication first, and then you add. Otherwise, you leave it alone, just like that. Don't forget this property here. A plus B over C is equal to A over C plus B over C. And you have done problems like that in the past. There are times when binomials containing radicals do not have the patterns of difference of two squares or perfect square trinomials. They're just binomials multiplied together. Let's look at this problem. In this case, you just use the FOIL process. So let's go through this and see what happens. We had the first terms, 5 square root of 2 times 3 square root of 2. We have the outer terms, 5 square root of 2 times the square root of 3. We have the inner terms, oh, I'm sorry, wrong arrow, right there, square root of 3 times 3 square root of 2, right there, the inners. And we have the last terms, square root of 3 times the square root of 3, right there. This is probably the hardest part. All right, now we got to do simplify. 5 times 3 is 15. Square root of 2 times the square root of 2 is square root of 2 squared. 5 times the square root of 6 plus 3 times the square root of 6 plus the square root of 3 squared. Simplifying more. 15 times 2, 5 times the square root of 6 plus 3 times the square root of 6 is 8 plus the square root of 6 plus 3. 15 times 2 is 30 plus 8 square root of 6 plus 3. Adding together, we get 33 plus 8 square root of 6. Remember, once again, I'm going to tell you, do not add those together. If you had an expression something like this, 4 plus 5a, there's not anyone in the class, I would hope, that would say that's equal to 9a. Remember, you can't add them because you don't have a common factor. If you had an a over here, you could, but you can't add those because before you add, you have to multiply. And you can't multiply until you find out what a is equal to. Once you find a, then you multiply the two together, then you add the 4. Similar, the same thing with this square root of 6. We're not going to find out what the square root of 6 is equal to. We're just going to leave it like that, multiply by 8, and then add the 33. Your assignment is 545, numbers 1 through 34, odd only. As always, you need to show the work where appropriate. I hope that I've given you enough examples to do these problems. As always, read the instructions in the book, read the examples. There are a couple videos, I think, on the sidebar on my wiki that will take you to a video on YouTube that will further explain this if you need it.